I told you guys to read the last section of the chapter, but I've decided to actually make it into a video because there's a couple of things in there I want to talk about. So actually read the last section. It's one of the few sections that you can count on for numbers. So the last section deals with what should be done, and in the side they're all like unplug things and ride your bike. But I want to talk about the more scientific aspects, and one of them that is of interest lately and getting a lot of press is geoengineering, which is the attempt to manipulate global cycles in order to offset the amount of CO2 and other climate gases we put out. So they do this two ways. One is to increase atmospheric albedo, and this diagram you see on the right is actually a design right here. The idea is this atomizes seawater up these towers. This is an unmanned yacht. It's supposed to run on solar power, and by atomizing seawater, it causes clouds to nucleate around those seawater, the water and the salt molecules, kind of like seeding clouds when they're trying to make it rain, and that would increase albedo, reduce the amount of incoming radiation, lower the temperature. This one is not actually being done on a large scale anywhere. This is very theoretical. And the other one is removing greenhouse gases and sequestering and sinking them elsewhere. So I actually have, hold on, I have a pop-up. I actually have a picture of this. So this is from the EPA, and this is their drawing. And the idea is that here's a power plant. And notice, I think, let me go back a slide. Here's a power plant, and notice it still has smokestacks, but nothing's coming out, right? There. And so instead of the smoke coming out of the stacks, it's being trapped. That's what these lines represent. And it's moved off site. And these are called injection wells. And they have to dig down really far past what they would call an impermeable seal. This is some sort of rock layer where there's no exchange with surface waters. They would inject that carbon dioxide into that layer, and theoretically it would be sequestered. It would be out of the area. There's concerns. They're doing this actually in Sweden already. They're injecting them into underground lakes that don't exchange with surface water. They're becoming wildly acidic. So the idea is that you would trap this. Fortunately, as you can probably heard about Oklahoma, everything is fundamentally subject to plate tectonics, and theoretically this stuff could come back up. So what's the ocean's role in offsetting climate? We've talked before about how much the ocean can absorb temperature. That's this idea of the thermal sponge. Water has a high heat capacity. People are literally just counting on it to absorb a bunch of heat. Also, we talked about how the biological pump of the ocean allows the movement of carbon dioxide from surface waters via primary productivity into sediment when we have that marine snow. And on geological timescale, 99% of all volcanic emissions of CO2 have been sequestered by this biological pump. So this idea of moving atmospheric carbon dioxide to surface waters, being taken up and becoming organic, and then going into the sediment is something that's happening already. There's some ideas to increase that. So this is one of those ideas, and as you can see, I wrote a lot on this slide because this is something that is near and dear to my heart. And the idea is called the iron hypothesis. So there was this guy, John Martin, who initially noticed that there were these areas of the ocean that should be very biologically productive. They have a good amount of most nutrients. They're warm. They have a lot of sunlight, but they have very little primary productivity. And he called these high nutrient, low chlorophyll zones, which I'll just call HNLC. And what he found was that they are missing one key nutrient, and that nutrient is iron. Iron is not particularly soluble in water. So especially in the Pacific, where there's no sources of iron, there were areas that were just dead, basically dead at the surface. And he found that if you took organic iron, like in an organically accessible form, and seeded the ocean with it, you would have these massive plankton blooms. And in this diagram right here, you can see where this is actually a coastal area, but then they seeded this area right here. And this is a measure of chlorophyll A. And the dark red area is so strong that the sea whiffs can't actually measure it. And there have been several experiments about this in the past 10 years, maybe 15. Southern Ocean Iron something experiments. And then SOFEX, which was run by Rutgers. So obviously that's why I know about it. It stands for Southern Ocean. FE is iron, and then X is experiment. And these were really successful. They were able to cause such huge blooms of plankton that when there was the subsequent die-off, that they sank faster than they could be eaten. Because if they're eaten, they're just now part of the food chain. They would sink faster than they could be eaten, and they become part of sediments and thus locked away and no longer part of the carbon cycle. And this was wildly successful. There are some concerns about it, though. One of the concerns is that one of the plankton that bloom excessively at this point is a plankton that is toxic. The ciguatera planktons respond very well to iron. Also, we're changing the biomass. If you're causing a whole lot of primary producers to grow, they're not always going to be in the same ratios, and it may cause other cascading effects down the food chain. Besides the plans, whether it's injecting carbon directly into the ground or increasing the ocean's absorption of carbon, the other main aspect people want to change is to limit emissions. And there have been dozens of international conferences where they meet to try to get a grasp on limiting emissions on a global scale. The most famous of which is the Kyoto Protocol, which was in 1997 and named for where it was found. As of right now, 122 nations have agreed to the Kyoto Protocol. And basically the idea is that industrialized nations agree to reduce their emissions levels to 5% lower than 1990. And we signed it. We agreed to it. We ratified the Kyoto Protocol. In 2001, which you'll recognize as the year after an election year, President Bush at the time backed out, and he cited economics. And the big idea here was that China hadn't signed the Kyoto Protocol. They are the largest emitter of greenhouse gases. And if they weren't going to do it, if we did it, it would be an economic problem for us. So we've backed out. Many states actually then went ahead and signed the Kyoto Protocol individually, including our state, New Jersey. About 7 years ago now, a new governor came in and backed us out of the Kyoto Protocol. Additionally, just in the last week, we've dropped out of the RGGI Protocol, which was the one I talked about when we were talking about cap and trade. So just because these get agreed to doesn't mean anybody's doing them. This is a graph from the EPA, and it basically shows U.S. emissions. They peaked in 2005. That was the highest amount we'd ever put out. Since 2005, it's been steadily declining. And as of last year, our emission levels were just 6% above 1990. It's not great. It still puts us at the second largest single country for emissions, but it's better than it was. We can confidently say we're beginning to level off. But China's not. China's expected to continue. Right now, they put out a third of the world's emissions functionally. One nation. That's expected to go up to almost 40, some predict 50% in the next 10 years. They are opening a coal-fired power plant a week over there. But just in the last month, President Obama got them to agree to a cap and trade that will be set to emissions level set in 2017. That's still a lot of greenhouse gases, but it's better than it was. So I guess we can say we're making progress with limiting emissions. This graph has to do with the sectors. This is just the U.S. and where most of our greenhouse gas emissions are coming from. A lot of people think that it's cars, and this one bothers me. Cars are actually a small fraction. This is us. That would be cars, transportation. But the largest chunk of the transportation piece of the pie is actually comes from shipping goods. So like when you buy shoes and they were made like in Asia, there's a greenhouse gas emission associated with that. So then if you notice, the other big ones are going to be agriculture, and the biggest is electricity and heat production. But of this electricity and heat production, half of it is in industries and commercial buildings. All of the people in the United States only account for half of that, this piece of the pie, in their homes, which is weird to think about when you think about, how many people there are. And I put this link up here, the Science Daily link. A group of people up in MIT did some, back of the napkin calculations and found out the average American gives off 20 tons of carbon as their carbon footprint a year. Even if you stopped doing anything, buying things, like the lowest they found were for homeless people who live in shelters and eat from a soup kitchen, they still put off 8.5 per person tons of carbon dioxide a year. And that seems weird, but you have to think about all the infrastructure. They are citizens of this country, our roads, our military. We each get a little piece of that pie that's part of our footprint. So there's a limit to how much a person can change, how much their personal footprint is. And I think you guys got this from the game, that in order to make real change, we have to do regulatory stuff on the part that belongs to industries and whatnot. Yeah? All right. So the last thing in the book is the end. So people seem to act like if we don't stop greenhouse gas emissions, we're going to have Okay, so where was I? I was saying that greenhouse gas emissions are frequently paired with the end of the world. This world has been through many changes in climate. We've talked about the Milankovitch cycles, ice ages, and glacial minima. That's not really the concern. The concern is that this particular climate change has a threat to remember, 80% of people live within 60 miles of the ocean. And 10% of people in the entire world, including in this country, a good portion, live below the floodplain. Those people are wildly at risk to not just sea level rise, but also storms. Additionally, 3/4 of all large cities are next to the ocean directly. Large cities tend to have large populations. So the effects of this climate change could be felt disproportionately compared to the landmass. People live near the ocean. So in order to protect our way of life, that's why the book is saying, we got to change everything. We'll talk more about things that you can do, but that ends the science part of this chapter.